There we go. So telescope array is up here, and today we are down here. So we're up in sort of the west central desert of Utah, about 39 degrees north and 113 degrees west. So this is a map of the telescope array. The original part is the green part here. 507 scintillator detectors and 3 telescope stations. And then we added a low energy extension, and we're currently in the process of adding high energy extension out here. So the telescopes are 2 or 3 meter segmented mirrors, and they focus the light onto cameras. 256 photomultiplier tubes are the pixels. There's a UV bandpass filter that goes in front of them, and pixels view about 1 degree of the sky. The scintillator detectors are 3 meters square of active area, 2 layers of half-inch scintillators, and they get read out by wavelength shifting optical fibers that are strung through grooves in the extruded scintillator. So this is what the scintillators look like when they're deployed out into the desert. And here you're looking along the diagonal. You see 1, 2, 3, 4, 5 way back there. So powered by solar power, readout by radio, calibrated by muons. The original array is on a 1.2 kilometer square grid. The low energy extension is 600 and 400 meters, and the new TA times 4 high energy extension is on a 2.08 kilometer square grid. There we go. So if you were at ICRC, you sort of saw this already. This shows the telescope array, the high energy part of the spectrum, and it's compared with these orangish dots, which are the Auger high energy part of the spectrum. And we've long known that there's a shift, sort of 9% between telescope array and Auger, and people usually just shift telescope array down halfway, and the Auger spectrum up halfway, sort of 4.5% each. But what Professor Oguio did was said, well, what happens if you modify the telescope array analysis so that you use the fluorescence yield that Auger uses, and also use the Auger missing energy correction, and then that yields these red points, which then agree within sort of 1% with the Auger spectrum up until about 19.5, 10 to the 19.5 EV. Uh-oh. The meeting has been enabled. Okay. So that's one way you can do this and get a good agreement, but not at the highest energies. So meanwhile, TA times 4 has been collecting data. This is a measurement by Kozo Fujisue, and using the first 3 years of TA times 4 data, he compares his spectrum with Auger, which is the open circles, and the standard TA spectrum, and he gets good agreement with the TA spectrum. So that's not going to solve the difference at the highest energies. So one of the things we did more recently is we fit a combined fit to the full Auger spectrum and the full TA spectrum over the full apertures, and that's the red line here. And then on the left we overlaid the Auger spectrum in the full aperture, and it's not a bad fit. It's a little bit low, as you might expect, because the TA points are higher, the Auger points are lower. If you compare the TA data in the common declination band, there's obviously significant excess over here. The common declination band is this band from -15 to plus 24, 20, almost 25 degrees declination. And that's where you would hope that telescope array and Auger would agree in the spectrum. So this has been studied by Dmitry Ivanov, and what he said was, what happens if we take and divide the telescope array spectrum to two parts, one in the common declination band and the other above the common declination band? And what he finds is that in the band above the common declination band, so the top part of the aperture, the cutoff is higher and the fall off is steeper. In the common declination band, the cutoff looks a lot more like the Auger cutoff, but the slope is significantly different. If you go back and compare what you expect sort of out of the slopes, you expect the slopes to be pretty similar, but just dividing the common declination, the data into common declination band and not common declination band, you get a relatively different slope. These two spectra are different at sort of the 4.4 sigma level, so that's beginning to be significant there. So one thing that we know is that telescope array sees a couple of excesses. One of the excesses is this hotspot, which in the first sort of 5-6 years of data was relatively bright. Not so bright more recently, but still some excess there. More recently, there's a lower energy excess, 10 to the 19.4 EV, sort of here overlapping with the Perseus Pisces supercluster. So if you look at where those are in the sky, the hotspot is up here, and Perseus Pisces supercluster is here, and the common declination band is drawn by these two red lines. That's where telescope array and Auger see the same part of the sky. One can argue, and I would, that below this blue line, the aperture, the exposure for telescope array is dropping quite rapidly. And those events are a little bit more poorly reconstructed. The spectrum is a little bit more poorly reconstructed. I suspect that the Auger data at the top of this common band has the same effect. So if we look at what does the telescope array spectrum look like inside the hotspot, inside the excesses versus outside the excesses, and compare them to the Auger spectrum in the full sky. The Auger spectrum in the full sky is these blue lines. Inside you see, as you might expect, a big excess over here in the high energy band. Outside the two excesses, there's still some bump, but they're a lot more in agreement. So if we remove those two excesses and then also remove the more poorly reconstructed spectrum sort of below that -5 degrees declination where the aperture and exposure are falling off quite steeply, now you can see that the telescope array spectrum is much more in agreement with the Auger spectrum. They now agree at sort of the 1.8 sigma level. So this is obviously something that's important. And Could be that those excesses are just statistical fluctuations, could be that those excesses are real sources. And at this point, we don't really know. We need more data to actually figure that out. So hopefully most of you saw that telescope array observed a very high energy event. And this is that event. Oh, what the scintillator detector array saw. The circles are the signal in the scintillator detectors, and color is time, size is amount of light or number of particles. This is a huge event, sort of 240 EeV. If you figure out where did that come from, well, it comes from someplace right out here, out in the middle of nowhere. There's nothing really out there. You expect these really high energy events to come from something. It doesn't. If you say, well, what if it's not a proton? What if it's carbon, silicon, iron? You compare to different magnetic field models, still you're having a really hard time to figure out what's the source of this. If it's this high in energy, you expect you should be able to find the source. Should be something reasonably close. So meanwhile, we also took all of the events, reconstructed. This is a plot from Toshihiro Fuji at ICRC. The TA events are at the top. TA events above 10 to the 20th. At the bottom is the Auger events above 10 to the 20th. And these events don't seem correlated with the distribution of matter in the universe. There was a recent paper that's in the process of being published in PRL and PRD, where our Russian colleagues went through and looked at the events above 10 to the 20th, and they conclude the same thing. That's not correlated with the distribution of matter, or the magnetic fields are wildly different. To make things match, you got to say that things are heavier than iron. So this is crazy. This is something we need to collect enough data and really understand. Meanwhile, telescope array, this is the data. Whoops. Yeah, this is a little insensitive. Compared to QGS Jet 2-4 protons, nitrogen, helium, nitrogen, iron compared to the data looks light and constant as far as we can tell. Some fluctuations out here where statistics are bad. We also tried doing a composition with a boosted decision tree on the scintillator data, where you have more statistics and you can go out to sort of 10 to the 19.7 or so. And this also agrees with a light sort of proton helium composition. This needs to be better correlated with the hybrid data, but that's what things are saying so far. More recently, we've been doing composition with TA times 4, and this is the result of graduate student Zane Gerber. And again, comparing to QGS Jet 2-4, comparing to protons, helium, nitrogen, and iron, looks sort of right in the middle of protons, helium. Can't really tell what's the difference there. On the other hand, there's a joint Auger-TA working group that they're trying to understand what's going on also. And TA can take the composition, which Auger gives us sort of a mix of protons and heavier elements, and then we can regenerate the Monte Carlo using Sybil in this case, and then reconstruct that data, that Monte Carlo, and compare it to the data. And this is This is the comparison of those two analyses, the Auger mix reconstructed and the TA data reconstructed. And yeah, maybe they're starting to disagree, but by and large, they sort of overlap in the sky. And so if they're at the same point in the sky, then you got to say, well, how does all this fit together? And I'm still trying to figure that out. So telescope array and also Auger, we both looked for protons and neutrinos in the data. And so far, all we've been able to do is set limits and no photons or neutrinos found. One of the other things that telescope array is working on is starting to deliver some interesting results is lightning. So early on in telescope array, one of the students from Osaka looked at the data and said, there's data in the scintillator that doesn't make any sense. It's all mixed up. It extends over huge amounts of time compared to a cosmic ray. And eventually he figured out these are gammas that are coming out of lightning. So more recently, we've added a whole bunch of electric field measurement devices and some really high-speed cameras, like 40,000 frames a second. And we look at what happens with lightning, and then we look at the signal of what we see on the surface in the surface array. And you can correlate those two. And even now they're starting to do spectral measurements of what does the light spectrum look like coming out of that lightning at different phases of the lightning as the breakdowns occurring. So this is sort of a side interesting field that you can pull out of telescope array data. So telescope array measures spectrum over more than 5 orders of magnitude in energy. We find a significant difference in the high energy spectrum above and below 25 degrees declination, sort of the common declination band. There's now an 8 sigma difference between the high energy spectrum observed between telescope array and Auger in the full field of view. And the difference in the common band can be reduced to less than 2 sigma by cutting out the data from the excesses and that exposure edge. The hotspot persists, but the significance is not increasing very quickly. It looks certainly a lot less bright. There's a lower energy excess in conjunction with the Perseus-Pisces supercluster. Using QGS Jet 2.4, the composition appears to us to be light and steady, but when we compare to a Sybil generated and reconstructed Auger mix, they look like they're in a similar height in the sky. There's a new high energy event, which is 2.4 times 10 to the 20th. And the thing I really find exciting about that is it's approaching now the energy of the fly's eye, oh my God particle at 3.2 times 10 to the 20th. And observed by, very different techniques, one by scintillators, one by fluorescence. So this is, nice verification that these events do exist. And when we look at events above 10 to the 20th, they appear isotropic. So this is a puzzle that we need to solve.
Thank you very much, Professor. We have time for questions and comments. Karl-Heinz was the first.
Thanks for the nice overview of the TA data. I have a question. You showed that the energy spectra in the hotspots look differently. They have the bump, which is not in the other part.
It's a lot bigger there in any case.
And my question is, did you also look at the X max, at the composition in that area to see whether
we have not looked at that, and it needs to be looked at. Although the statistics are going to be really bad, but I'm like you, I'm interested in that.
Yes, yes, would be interesting, even though with limited statistics. But-
Yeah.
Okay, thank you.
Well, it's thanks for a nice talk. I'm very happy to see that when you remove these edges, exposure edges, and the excess region, that at least the two of them have come closer together, which is very gratifying. But you mentioned you need to collect more data. Of course, that goes without saying. But really, realistically speaking, given the, you really need a large area, right? So realistically, do you expect with telescope ray times 4 and the present Auger, we can hope to see higher statistics in reasonable future? Or does one really need to make an argument for a maybe order of magnitude increase in area? That's always going to be the important
I think
question.
I think a handful of years with TA times 4 will make a significant difference, but in the end, you're going to really need a much bigger detector. Preferably something that sees both hemispheres. You really got to sort that out.
Alf?
Thanks a lot, John. Yeah, now from my side, I would like to just to sort for myself in my, let's say, view and also for the audience. So you have the joint working group, and if you could show the slide again.
Which slide?
The joint working group with X max, with the depth of shower maximum. Yeah, no, this was already the slide, one back maybe. Forward in your direction, probably. Yeah. That's not, well, I thought you showed it towards the end of the talk. Because I'm interested to see the energy range where we have agreement in the composition. The arrow keys should work, yeah.
This one?
No. The joint working group on X max, like Alexei Yushkov et al.
Oh. Sorry, X max.
This one.
This
yeah.
one.
Because it's my understanding that two collaborations will bring out a paper very soon.
They're trying.
Yeah. Let's hope that's going to work. And we do have agreement in the composition in the study, because you see the points are TA points and the histogram is Auger in X max. And we do have agreement in the composition up to maybe, I don't know whether the last bin we can say anything about it, but maybe 19.5 in the direct measurement. This is my understanding of this work. Of course, it doesn't mean that we have the same composition at higher energy. That's a different story.
Says you see them at the same point in the sky.
Yeah, no, it's so for the X max, of course, I don't know what the sky exposure for TA would be relative to Auger. Maybe then that's an interesting question still to see from what parts of the sky this comes. But we do have agreement now after many years of work, and that's very good, this agreement. Both are compatible. And if you now go to the SD data, it looks like we have a large discrepancy in this energy range where we find X max agreement.
Yeah.
I only want to point out that this is this one. Because in the range of 18.5 to 19 point something, we have almost perfect agreement between Auger and TA, at least what X max data concerns. And so what you see is something else, or I really don't know. Yeah. So that part, I agree with you. It's something we need to understand, but at least the fluorescence data, the shower maximum is the same.
Looks like it's in the same part of the sky. Yeah.
Whereas the surface data, and then, well, I can tell you that Auger has done the surface data composition analysis, and we are 30 grams off if we use neural networks in Monte Carlo. And we have to calibrate with our fluorescence data to correct for that. We know that our simulations don't describe the footprint correctly. So I would say if you don't do a recalibration or a cross-check of your surface data,
Yeah, and I'm
the
not quite sure,
fluorescence-
I'm not quite sure where that is, and I need
Yeah,
to
you-
find
you-
that out.
well, for
I've
us,
been
this
trying to,
was- Yeah,
yeah, this was a student that now abandoned. And
Well,
so now I've been trying to find her and get her to answer a few questions.
no, but the constraints.
No,
we
yeah.
also have them in
Yeah,
OJ. It's but I only wanted to say we have to take this with a grain of salt because
Yeah.
that's coming out of the box.
Well,
But OJ had to recalibrate by 30 grams, and that's a third between proton and iron. It's a big effect, and so you could have a similar thing, maybe to a less extent. I don't know, but you need to cross check. This
Yep.
is our message
Agreed.
that we learned the hard way in OJ. Yeah.
agreed.
Okay, thanks a lot. Yeah, I only wanted to point out that it's
No,
not
yeah.
looking like the two experiments see really different things. Yeah.
Well,
So it's
this-
a little
yeah.
bit more complicated, and so one shouldn't get this impression. But the spectrum is definitely something very, very interesting. We should look at and understand better. And yeah, well, we will have to work on this. Yeah. Thanks a lot.
Thank you, Ralph. Sergey.
Just a minor remark. When you speak about similarities or differences, one has to quantify them. If you please come back to the slide from Yushkov, look at the distributions. Actually, it's not too high energies. No, yeah, right. Look above, not too high energies. In TA data, we see that scope events going very deep. They're not many, but they make strong impact on the width, on the sigma X max. And actually, it's a peculiarity of AGIT data, one doesn't see that. There was even a paper from the collaboration initiated by Zigging Group, studying these tails and putting upper limits on proton and helium.
We have just few minutes for questions from people connected in Zoom. Are there questions from people connected? Could you please raise your hand if you have a question? So there are no questions. So we thank again, Professor John. It was very interesting. And I think we are continue discussing about that during the whole meeting. So our next talk is about Hawk and is by Daniel Omar Avila Rojas, who is going to present the recent results from the Hawk Gamma Ray Observatory.
Pronto, yeah. Yeah, can you hear me, right? Okay. Yeah. Okay, so well, thank you for the invitation. My name is Daniel Maravilla Rojas, and I'm working at the Instituto de Astronomía in the Universidad Nacional Autónoma de México. And I'm going to talk you about the recent results from the Hawk Observatory concerning cosmic rays. So, yeah, it's not working right. Okay. So first of all, the Hawk collaboration is a collaboration that have 38 institutes from all around the world, and mainly from Mexico and the United States. And well, Hawk has been in operations for about 10 years. And well, we just have recently in April our collaboration meeting, and there we present most of the recent results. So now about the Hawk Observatory. So I think most of you know what Hawk is, but well, I'm going to just make a brief review about it. So Hawk is an gamma ray observatory that is located
Okay, so Hawk is located here in Mexico at Sierra Negra, that is in Puebla, and it was constructed at an altitude of 4,000 meters above sea level, and it has a geometrical area that is about 20,000 square meters. And the thing about the selection of the site is because we were interested in some energy range in which the air showers get its maximum just at this height. And well, it was constructed with 300 water cherry cup detectors, and later it was implemented with 345 outrigger detectors. Well, these outrigger detectors are still being characterized, and we are just still working only with the 300 water cup cherry cup detectors. And well, the water cup cherry cup detectors have this specification. They have a diameter of 7.3 meters, a height of 4.8 meters, and each of it is filled with 200,000 liters of purified water. And at the bottom, we have these 4 PMTs, so we can recollect the Cherenkov light that is generated by the secondary particles from our air shower. And well, with this, what do we have? We are capable to have a gamma hadron separation or identification in this case. And here I'm showing you 2 different kind of events, one generated by a photon and one generated by a proton. And what we have is that the time that we have of these events that coming are really smooth around the core that we can reconstruct. While when we are checking about the proton, we have that this distribution is not that as smooth and is characterized by these hotspots that are mainly muons that come and deposit a big amount of charge at these detectors. And well, by using this, well, we just check on the arrival times from the shower, and also we check for all the charge that is deposited in each of the PMTs. And with this, we can have an image of the shower, of the lateral distribution of the shower, and we focus on which events have high charge deposited around 4 meters from the core. And this is one of the ways that we can check if it was an event generated by a proton or generated by a photon. And also we have now implemented an energy estimation method. So currently we are working with 11 energy bins, and each of these bins, well, we are mainly using from bin B to bin L. We are still working in better algorithms to understand better this low energy regime. And also we have 2 different methods that we can use to estimate the energy. One depends purely on the charge deposited in the PMTs from a certain distance from the core. And this is called the ground parameter method. And the other one is by using artificial intelligence algorithms. In this case, we're using neural networks. And well, both of the methods are really consistent. And well, it only depends on what do you want to analyze for deciding which one of these methods you can use. But both methods are consistent within each other. And well, I think that is the only thing that I wanted to talk about the Hawk detector. And now I'm going to focus on the recent results from this Hawk experiment. And the first thing that I'm going to talk about is the cosmic ray spectrum. So for the cosmic ray spectrum, we have made this analysis of the all particle cosmic ray spectrum. And well, this was in 2017. And what we have is that we simulated all of the part of the cosmic rays from light from heavy flavors. And well, what we have here, the Hawk data points are this one in blue. And we see that they are in agreement with the cosmic ray spectrum from other experiments, just as Attic and Grapes and and other of those. Well, and here we put as a reference the light particle spectrum measured by CRIM. And well, one of the highlights of this result is that we seems to have a spectral break around 50 TeVs. And well, we just needed to check whether this break is statistical significant. And well, that was made just a few years later. Well, in fact, the PAD result that I told you about was only taken around 250 days of data. And this one is with 4 years of data. So, well, what we did is check only for the light component of the cosmic rays, specifically only protons and helium. And we check the spectrum in this energy range. And what we see is that, in fact, we are still seeing this spectral break. And well, it was shifted just a little bit. Before it was around 50 TeVs, but now what we have is that it is around 10, 20 TeVs. And it was previously reported, and it was now confirmed by, with all other larger ES data sets that we have taken, and also with improved simulations. And well, this break is, as I told you before, near 24 TeVs. And what we see is just a softening of the spectrum, and the decrease goes really smooth. It goes from this spectral index of 2.51 to 2.83. So this is one of these recent results. And when we compare it with other experiments for the light component of the cosmic rays, we see that it is really in agreement with the other experiments, precisely with Attic, CRIM, and Nucleon. And also, DAMTE has a result that is in agreement with this softening of the spectrum at around 10 TeVs. So, well, now about the anisotropies of the cosmic rays. What we have is this previous work of 2018, where we check the anisotropies at large scales and small scales at different energies. So, well, as we see at high energies, these anisotropies just start disappearing. And when we check for the small scale anisotropies, we get these little hotspots. So these hotspots has been, in fact, observed by other experiments. In fact, Milagro, I think, was one of the first that checked these regions. Well, and well, we have the region A, that is the most prominent of all of these regions. Region B is also is not that significant, and region C. But the improvement in this analysis is that we get new insight of this other region that wasn't detected previously. And well, it's weaker than the others, but well, it was just discovered with this work. And well, the other work that has been made about the anisotropy of cosmic rays was made using Hawk data and IceCube data. And well, we did this collaboration and focus only on events that have a median energy of 10 TVs. And well, when we make the merge of all the data, we have that the full sky observation just get rid of the degeneracy between the spherical harmonical components. And well, when we check at small scales, well, we see also all these regions, and well, in fact, at large scales, you can see here the local interstellar magnetic field line is here depicted at the with this black line, black solid line. And as you can see, well, the deficit and well, the excess that we see are kind of perfectly separated by this line. And well, still we need to check what is one of the causes of these excesses that we are seeing at small scales. So this is work that we're still dealing with. And well, the last topic that I want to talk to you about the recent Hawk results is about the cosmic ray accelerators. So as I said it before, we are concerned or really interested in try to identify these cosmic ray accelerators in the galaxy and also of extragalactic origin. But here I'm only focusing on those from galactic origin. And well, this result was published in 2020, and it was just after we make one of our catalogs. I think it was the third catalog, and we detected several sources that have an energy above 56 TVs, and also some other sources have significance above 150 TVs. Well, I'm talking here about gamma ray emission. So, well, if we have sources here in our galaxy that can reach these high energies, such as well, a few hundred TVs, we have several hypotheses of what is the cause of this particle acceleration that maybe produce these gamma rays. And well, we have two models. Well, in fact, there are three. Well, the leptonic model, where we have electron positrons that are being accelerated in diffusive shocks, or hadronic models, where we have also mainly protons that are being accelerated at relativistic energies and are able to produce gamma rays via pion decays. And the other scenario that we can imagine is just a merge of those of these two, a leptodronic scenario. And well, from all of the sources that we detected at these high energies, we start to make an analysis on those sources that can have this high energy and maybe possible cosmic ray accelerators. So the first one is this source, J2227 plus 6010. And well, this source is in a really rich populated region. We have, I'm not quite sure how many pulsars, but I think there are 2 pulsars and also 1 supernova remnant in this region. So, well, in fact, for the leptonic scenario, it is assumed that this electron positron acceleration mainly occur on the pulsar wind nebula or by pulsars. And for the hadronic scenario, we believe that it is mainly the gamma ray emission is mainly generated at the supernova remnant by diffuse acceleration in shocks. So we need to try to identify which one of these scenarios is the one that can explain the emission of these high energy TeV photons. And well, sorry. And well, concerning this region, well, we checked whether it was generated this emission by the pulsars here in this region or by the supernova remnant. And what we have is that the more favorable scenario is that one that is assumed by is by assuming that the high energy gamma ray emission is generated by protons in the supernova remnant that is known as G 106.3 plus 2.5, 2.7. And well, also we can interpret this emission from both hadronic and leptonic emissions. And one thing that we need to just discard any of these scenarios is just to make multi-messenger analysis. In fact, what we really need is that if we have hadronic emission, we need to have correlation with neutrinos. So, well, we need more results from these neutron experiments like IceCube, but well, just by checking the spectrum, we can see that the spectrum reaches hundreds of TeVs, and when we assume an hadronic scenario, we get that the proton spectrum must have a cutoff energy above 800 TeVs. So this means that this source could be a galactic pevatron. So we are still working on this interpretation, and well, we, as I said, we need to check if this scenario is possible, and well, this is something that I'm going to tell you later. And well, for the other source that we have is the source that is called HAWK J1825-134. And also, as you can see, most of the sources that we have at high energies are in rich populated zones. So here we have three sources that have been detected, but one of these sources extends its spectrum up to 100 of TeVs. So from this, we check in this region what else is around. And well, what we have is that there's a lot of sources again. There are many pulsars. And one thing that we have here is that we have a region that is associated with a giant molecular cloud. So we check whether the leptonic or hadronic model was favored. And what we have is that the favored scenario was PV cosmic ray protons colliding with the ambient gas. And this ambient gas, here I'm showing you the columnar density of this gas, and is associated with a young cluster, a young star cluster. So, well, we identified that it is possible that this cluster may be another pevatron. And well, the other source that is really interesting of the recent results from HAWK is the region of the Cygnus cocoon. And well, this region is characterized by a massive star formation rate in a bubble region. So we also have a lot of sources here. So we get rid of all of the hotspots, well, of the sources that are contributed here. And after getting rid of this signal, we are still getting an excess. And we name this excess as, well, this source, J2030 plus 49. And, well, we check for the spectrum of this region, and, well, it reaches high energies also. It extended above, well, 100 TVs. And we check if the emission may be generated here in the bubble, more specifically in this star formation zone, where we have, in general, OB stars. And well, the OB stars are characterized by high winds that may be the possible explanation for a region of gas that where we have these interactions. And well, one of the last studies that we have made from the possible cosmic ray accelerators is of the one concerning this Hawk source. And well, we check for all the possible scenarios, as I told you, the leptonic, hadronic, and also leptadronic scenario. And well, the possible origin for this source is, again, there are a lot of other sources that may be correlated with this emission. And we have a pulsar there and a supernova remnant also. So the thing with this source is that both of these scenarios are really plausible. So we need more data, more joint analysis with other experiments, so that we can get an idea if this gamma ray excess is really due to a leptonic scenario or an hadronic scenario. And well, there are many other works about cosmic rays in the Hawk collaboration. I think I'm do not have the time to talk about all of these works, so I'm just put you this in this slide so you can access all of these works. And well, one that I want to mention that I think is quite interesting is this one, the characterization of the Hunga pressure wave with cosmic rays by Hawk. I don't know if you know about this Hunga volcan, but it was just a huge eruption that generated a shock wave that propagated all around the world, and well, we were able to characterize this by using cosmic ray data. And well, just a summary. Well, we have many cosmic ray studies that has been performed by using the Hawk Observatory, even though Hawk was think to be a gamma ray observatory, but well, most of the events that we have are mainly cosmic rays, so why not use that data? And we are still working on analysis techniques so that we can improve our gamma hadron separation and also our energy estimation. And well, the thing that I want to highlight here is that we have detected potential cosmic ray accelerators, and these are the mainly sources that we believe are the cause of this high energy gamma ray. We have supernova remnants, bubbles that are characterized by a massive star formation rate, and also star clusters. But these star clusters need to be well, rich of OB stars. And we have several other analyses in development and others under collaboration review. And we are making an upgrade on the cosmic ray spectrum and extending up to 10 to the 15 EVs. So, and We also are checking the composition of the cosmic ray spectrum, not only for hydrogen and helium, but also by implementing the heavy component of the cosmic rays. And this analysis is in progress. And also we are checking for an update on the cosmic ray anisotropy, so we can say more about. And we are also improving it with 8 years of data. And well, I think this is one of the most interesting. In fact, I think it's just on the last review from the collaboration, and is that we are testing the molecular cloud paradigm for one of the sources that I mentioned you. And this is by assuming that the protons are being accelerated in this supernova remnant. And I think in a few months, maybe it's going to be just published. So thank you.
Thank you very much, David. First question.
Very nice and comprehensive review. You had mentioned that these outriggers have now been installed, right? 375?
They're installed, but we are still working on how to analyze that data.
Okay, but they are working. They are on site.
Yeah.
So apart from improving the gamma to hadron separation, which of course it will probably help, are you also planning to use it for more precise study of cosmic ray composition? Because now you will have huge amount of information on muons, right, from these outriggers. If I just scale up the number, it's like 25,000 square meter of muon detection. So that will give you a very high sensitivity for elemental composition.
Yeah, we're hoping for, but we're still working on that. Yeah, but in fact, one of the other things that are helping us with the triggers is that we can have more high energy air showers. So yeah.
But the nice part is that you will overlap with direct experiments like AMS, which have measurements up to, few tens of TeV, and then you can really tune your Monte Carlo.
Yeah.
So that will be a great combination.
Yeah, we're looking forward.
Thank you. Are there more questions?
Just one comment about this Tonga volcano. In fact, in GRAPE, we have also observed and we compared your results.
Nice.
So there is going to be an invited talk after lunch. I'm sure it will be there. So yeah.
Nice.
Thank you.
No, thank you.
Just a minor question. In your previous to last conclusion, you speak about ultra high energy cosmic ray. I guess you mean pevatrons, right?
Yeah.
No, not ultra high energy. And the main factor, obviously, which stops you going up is the purity of your selection, right? Discrimination of protons.
Yeah.
With gamma.
Yes.
Yeah, thanks a lot. So from my side, I would be interested to understand, so you earlier showed cosmic ray breaks, and you said that you had a break at 50 TeV, and then it moved to lower energy. But my understanding was one break was the all particle spectrum, and the other break was
only
proton and helium. So there's no contradiction, right?
No.
Because so the break at 50 TeV is not ruled out in the sense of being a break in the all particle spectrum. Is it, or?
Yeah.
So you have not changed that. It's only that you are more specific now by going to the light component and seeing the break of the light component at lower energy.
Yeah, exactly. That's the only thing.
Yeah.
But it's consistent.
Which makes a lot of sense. Yeah.
Yeah.
Okay. Thanks a lot.
Yeah, just about the same point with the needs which you see in the all particle and proton helium component. If you look at the indices which you extract from that, I think if I compare that to data from Cascade, I think also the indices actually agree, right?
Yeah.
I just compared it to the published data. So it gives a very consistent picture. Of course, we don't know what the sources are for these different needs, but I mean, at least the data seem to be consistent
Yeah, it's
with one another.
really consistent within each other. Yeah.
So I will ask to the people connected in Zoom if they have some question, please raise your hand. No, there are no more questions. So we thank again David. It's very interesting. And now we have 30 minutes of coffee break, and then we come back with Karl-Heinz as the chairman.